Okay, so this morning we talked about writing strategies for getting students to start writing in the scientific discipline. This video is going to be all about making forms of scientific information that are in the forms of graphs and tables and being able to describe those appropriately. And so this is the activity tracking water using NASA satellite data. This is a NASA activity created by education specialists at the NASA JPL in California. And so they've recently created this. They've shared it for everyone to use. I think it's a really fun activity, and it relates to fourth grade and fifth grade like content standard application. And so I think that some of you will find this very useful, and then others, you'll get an opportunity to practice making tables, making graphs, and finding a way to make them appropriately for your own grade level. You can adjust the graph so that it's something that you feel like it's going to be something you'd rather use or get practice doing something that maybe is something you're not going to use, but will help you understand what types of, things that your students are going to want to be able to do in the future, so it can help guide your planning for some of the things that you're doing already. And so, yeah, it's going to be pretty fun. There is an activity you guys are going to do. I'm going to model the instruction of the activity in this session. You can complete the activity then after the session and submit it in the assignments when we're finished. So this activity is going to be a little bit different than like our journals. What you'll do is you'll collect the data through the process that I'll describe in this video. Then you're going to make a table, and then you're going to create a graph, and then you're going to stop until our teleconference. So at 3 p.m. on day number 3, which should be on Wednesday at 3 p.m., we are going to come up with a pre-writing strategy and do it together as a class. We'll do the pre-writing strategy. I'll lead it for helping us write descriptions for our graph. And then you're going to write a description. You're going to find a classmate to proofread yours, and then you're going to proofread someone's. And then in the assignment, you're going to submit not only your draft, but a draft of a classmates that you have proofread and suggestions you provided. And so check the rubric for that assignment if you want to start thinking about it ahead of time, or you're getting a head start on it, for the things that I'm going to be checking for in your proofreading, because I am going to check to make sure you've looked at someone else's and then provided them feedback. Okay, so let's get started. Tracking water using NASA satellite data. We're going to start with this video that explains what groundwater is.
We all know the Earth is full of water, but there's a lot more to water than all that blue stuff you see on the globe. The water we can see on the surface of the Earth is surface water. Surface water is every lake, pond, river, stream, and ocean on Earth. But in the ground below your feet, there's even more water, groundwater. Groundwater is water that's crammed in the tiny gaps between rocks, soils, and sediments under the ground. A full body of groundwater is called an aquifer. There are huge aquifers all across America. The biggest is the High Plains Aquifer, which covers 174,000 square miles right in the middle of the country. Anything that big deserves a closer look. Let's say you could grab a shovel and dig straight down through the soils to an aquifer. The level underground where you first hit groundwater is called the water table. Below the water table, the ground is completely soaked or saturated with water, which is why this area is called the saturated zone. The area above the water table is called the unsaturated zone. So, how does all this water end up in the ground? Well, it's all a part of the good old water cycle. When it rains, some water gets soaked up by plants. Some water runs off the soil and into streams, lakes, or even the ocean. Other water gets stuck on the surface and eventually evaporates back into the air. Meanwhile, some of the lucky water droplets get to travel down through the surface deep underground until they reach the water table and become a part of an aquifer. Once water seeps down deep enough into the ground, it can stay there for a really long time. Some of the water stored in the deepest parts of aquifers has been there for thousands of years. But after it gets there, groundwater doesn't always stay in the ground. A lot of the water on the surface comes from aquifers. If the surface of the ground dips below the water table, groundwater flows out into the space, creating a body of surface water. If the surface water dries up, groundwater can flow in to fill it back up. And if the water table in this area rises, so does the level of the surface water. Groundwater can also pour down a sloping surface, creating streams. Any place where groundwater flows out into the surface is called a spring. Surface water can also become groundwater. If a body of surface water flows above the water table, water can seep down through the sediment and help fill the aquifer. Of course, there's another way that groundwater can leave the ground: us. Humans depend on groundwater, and there are thousands of wells all over the country that draw water out of aquifers. In many parts of the country, the water you get from the tap comes from the ground. However, we use most of our groundwater to help grow the food we eat. Farms can get lots of the water they need from rain, but rain isn't always enough. And in dry years, farmers depend even more on the water that's stored in the ground. In fact, American farms use about 53 billion gallons of groundwater every day. That's enough to fill over 1 million bathtubs or 80,000 Olympic-sized swimming pools. So, if we're using that much every day, can it run out? Well, yes and no. Remember, aquifers can be refilled by rainwater or surface water seeping in from rivers and streams, so there's usually more water on its way to replenish the aquifer. But if we use groundwater faster than the aquifers can refill, we could drain them dry. They probably wouldn't be empty forever, but it would take hundreds of years for the largest aquifers to get back to healthy levels. Whether it's up here or down there, water and how we use it matters. We may not be able to see it every day, but groundwater makes our lives possible. So don't let show-offs like rushing rivers and roaring oceans get all the attention. Those unseen aquifers below ground have been here longer than we have, and with a little love and care, they'll keep on taking care of us long into the future.
Love that video. It does a really good job of taking the vocabulary words and providing students with an experience in the visual form in that video, and it's just really great. I love that. So we're going to now switch gears and talk about the GRACE mission, which is the Gravity Research and Climate Experiment. And this is an earth science mission that's being worked on between the United States and Germany. And so what is the mission? The mission is these two satellites, GRACE-1 and GRACE-Follow mission. And they orbit the Earth. They do it 16 times a day. And they measure small changes in the Earth's gravitational field. And by doing that, they're actually in turn getting an indirect measurement of where mass due to water is moving across the planet. And so you're a little confused about that connection between gravity and water. We're going to clear it up. So here's a little mission information from GRACE and GRACE-Follow.
Water is one of the main indicators of how the planet is responding to our evolving climate. We built our civilization around the climate that we had and the water resources that we had. And if those are changing, that can have a profound impact on how we operate our society.
GRACE and GRACE Follow-On measure the motion of water around the Earth, and they measure that in all forms of water. Water that's stored underground, water in the ocean, water that's frozen in the form of glaciers. So all of that together, GRACE can measure.
GRACE Follow-On is a mission to measure how water is distributed on the planet and how that changes from month to month.
GRACE stands for Gravity Recovery and Climate Experiment.
And it's a follow-on mission to this mission called GRACE that we launched in 2002. And that mission just ended a few months ago, and GRACE Follow-On is going to pick up and continue that science legacy.
So even though GRACE flew for 15 years, climate is one of those things which takes place on decadal timescales. It's really important that we look at these trends over longer time periods so we can establish the forces which are driving them.
One follows the other, and between them they accurately track the distance between the two satellites. And as they fly over changes in mass on the Earth, they move back and forth. And we track those little changes very accurately. And we do that with global positioning system satellite information and with star cameras that are on board the two spacecraft. I think there's an increasing awareness and consciousness around the Earth that water is a critical resource and that the sea level is rising, the polar caps are melting, and that all these have long-term ramifications on how we live.
The GRACE follow-on measurements give us very clear and tangible information so we can make sound decisions in the future of how we manage our resources.
Okay, so maybe that is clearing up that connection between gravity and mass for you some. Maybe not all the way, but we'll get there. So GRACE mission, you saw how it works, and so it generates maps called heat maps. Based upon that distance between the two satellites, the information is translated into heat maps. And so heat maps are maps that track how much of something there is in a particular location. And so it gets the term heat map because sometimes it's used to measure how much heat is in a location when it's measuring temperature, but not always. It can be used to measure quantities of other things. And so in this case, it's tracking changes in Earth's gravity field, which in turn tells science about the change in water mass for that location. And so the reason that is because if you think about the surface of the Earth for a moment, we've got rushing rivers, we've got oceans, we've got lakes, streams, and then we also have just at the surface where the soil is, we've got soil water, and then we've got groundwater also that's deeper down there in the soil, right? That is the only thing about the near surface of the Earth and the things within the Earth that change that much and change their location is the water. And so when water, a large amount of it, moves from one place to another, you can actually sense a change in weight at that particular location, or even a change in mass within the Earth at that position underneath of the satellite. And so that change in mass of the Earth causes the gravitational field acting between the satellite and the Earth to change. And so when it changes, that satellite either speeds up or slows down. And so the distance between the two satellites can be used to interpret the strength of gravity the satellites are experiencing when they pass over a particular location, which then in turn relates to the amount of water that's there, because that's the only thing about the mass that's changing in that particular location. It's not like mountains are built in one day to change the mass of that location, or that mountains are eroded or weathered and eroded away within a day to change the mass of that location. So daily, it's the water, the amount of water that changes in that location that's causing the change in mass. And so we can very creatively, through this process, measure the amount of water that is in a location. And so the GRACE satellite measures that in millimeters of water and gives a colored heat map to indicate how much is there. So 0 down to -20, all the way, or -200, all the way up to +200 are the color variations. And so this video is something that you are going to want to use for your data collection purposes. It changes. I keep pressing that and it doesn't play. There we go. It changes month by month. So it'll look like a video, but it's a monthly change of information. And so it's depicting the millimeters of equivalent water height with increased land water storage shown in blues and decreased storage in reds. So you'll see here that it's changing per month. And so we're in the year 2003. Now we're in 2004. Wow, we got a little dry there in West Virginia that time. There it got dry again. It was September of 2006. June, July, August, September of 2007, it's dry again. Getting wet again there in April, and then drying out again in September. So this will continue on until it reaches, I believe, 2012. Or the end of 2012. Okay, so let's unpack the data. And I messed up my slide there. I've got an answer showing before it's supposed to. So the question is, let's address what the heat map data is measuring. A, what are the units of measurement? So that would be, yes, millimeters of water. B, what does the blue color mean? That's where we have higher amounts of water than normal. C, what does the red color mean, or the orange color? That's lower amounts of water than normal, or than the average. What does the white color mean? Just normal amounts of water. And so question 2 is, why might it be important to track the amount of snow, surface water, and groundwater? And so I want you guys to think about that question, because the answer to that question is going to be important for our teleconference meeting later on today. So why might it be important to track the amount of snow, surface water, and groundwater? Why do we care to do this? Okay, so let's watch this one more video on the GRACE mission. Maybe this will help solidify your understanding of how those maps are created. And then we're going to use those maps to create a data table and to create a graph. So this is a way of communicating the results of this investigation. And so we're going to practice making tables, we're going to practice making graphs, and then we're going to practice writing descriptions of visual information.
Gravity is one of the fundamental forces of the universe, and it's connected with mass. Anything that has mass has gravity. We tend to think of the weight of the Earth as being entirely rocks and magma deep in the Earth. But actually, on the surface of the Earth, as you look around, you see the atmosphere, and you see the ocean, and you see snowfields and polar ice caps. All of those things have mass too. But those things change much more frequently. So what we realized is, if we could design a mission that was accurate enough to observe those small changes, we could actually watch the polar ice caps melt. We could measure polar ice mass loss. We could even measure how much water is in the ground after it rains. And that led us to come up with the GRACE mission. Deep in the Earth, or even on the surface of the Earth, the way mass is distributed with mountains and trenches and all kinds of things is slightly different, slightly non-uniform. So as you were to walk around the Earth, you'd actually sense more or less gravity. You actually weigh a little bit more, a little bit less on different parts of the Earth. Isaac Newton taught us that the amount of mass that I'm standing on top of affects the gravity where I'm standing. So the rate at which this apple comes down is a function of how much mass is below me on the Earth. So no matter where you are, what's below you will be different. So gravity will be different, and so the apple will drop at a different rate. The orbit of a satellite is highly dependent upon the gravity field of the planet that it's orbiting. So what we wanted to do was put up a satellite whose orbit we could measure incredibly accurately. The best way to do that was to observe one satellite with another satellite. So the satellites are sort of chasing each other, pole to pole, flying around the Earth. And as the first one comes up, for example, on a mountain, it feels that mountain first. So it starts to get pulled toward the mountain. But the second one isn't quite there yet, so the satellites tend to sort of drift apart. Then, of course, as they're leaving the mountain, the second one is still feeling the effect of the mountain. So they come together again. And that sort of dance that the two satellites do as they go around the Earth is what tells us what the gravity field underneath them was. Now, in addition to that, the gravity field is also changing every day, every week, every month, because water is moving all around the Earth and it's raining here or the polar ice cap is melting. So water is the primary thing that's changing. But what scientists really want to understand is not just what happens across 1 year. They want to really see that play out over many years, over decades, to try to understand what's really happening in the climate system.
We know that the world's distribution of water is being affected by climate change. One of the key things that GRACE data does is help us to monitor where the water is now and how it's changing over time. Before GRACE, it was nearly impossible to get that measurement. We would have to set up just an incredible array of equipment and an army of dedicated students and volunteers working several hours a day, a few times a week, year-round. And that wouldn't even be enough. GRACE is allowing us to see for the first time how fresh water is being redistributed across the continents. So here are the GRACE data. So what GRACE really does is make a map like this once a month, and the blue areas are areas that are wetter than usual, and the red areas are areas that are drier than usual. If the whole map were green, that would imply no storage change, so that would imply sort of a steady state. And for a long time, that's what people thought. And a lot of engineering and a lot of our infrastructure, storm drains, bridges, were built based on the idea that there were no long-term trends. And what GRACE is showing us is that there are these trends, that there are in fact storage changes, and that we have to deal with the changes. Let me point some of them out to you. Some of the biggest signals are the ice sheets, Greenland and Antarctic ice sheets that are melting away at a steady pace because of climate change. Some of the things we really just started to learn about are the decline of snow water storage in the Tibetan Plateau. That's a region that feeds many of the world's major rivers. We have the annual oscillation. We also have a trend, and that is an area where the trend is a linear decline. This is the Murray-Darling Basin in Australia. This is a basin that supplies a huge amount of water to the people of Australia. It's where most of their water resources are developed. And for as long as we've been looking at the GRACE data, that basin has been losing water. And it is not a good situation for the people of Australia. A surprise that we get from the GRACE data is that we're able to see groundwater mining, where groundwater is being removed from subsurface aquifers at a rate that's greater than it's being naturally replenished. One place where there's active groundwater mining is in the High Plains aquifer. Water levels have been in steady decline there for about 50 years. There's something like 1 billion people in the world today that don't have access to clean water. We need to be able to manage it. We need to be able to allocate it in ways that are consistent with climate change. And so GRACE can really help us track the distribution of water to help us better predict how climate and water availability is going to change in the future.
With GRACE, we have a new way to measure these things that scientists have been looking for so long. How much water is in the ocean? How much does the polar cap weigh? How much did it rain in the Amazon this year? You know, things that you think of as being very gut feel, physical measurements that turn out to just be hard to make any other way.
Okay, pretty cool stuff. Pretty creative way to observe the Earth. So here's another video from climate.nasa.gov. It's not as long. It's just a part of an Earth Minute, but I'm going to go ahead and show it. It's about GRACE.
Gravity. It's everywhere. It's the force that keeps our feet on the ground and the moon orbiting Earth. But where does it come from? Mass. That's simply the amount of stuff that makes up an object. The more mass something has, the more gravity it has. Earth's gravity is constantly changing because something with a lot of mass is moving around all the time. What's moving? Water and ice. If you've ever picked up a bucket of water, you've felt just how much mass it has. It creates a lot of gravity. Using satellites, NASA can measure Earth's gravity like a scale in the sky. By comparing one month to the next, we can track where the water and ice is going. Weaker gravity means there's less water in that spot. This can tell us where a glacier is melting or a severe drought is drying up lakes. And stronger gravity? More water, such as in the rainforest in the Amazon. Our scale in the sky even lets us measure water deep underground. Knowing where the water and ice is moving helps us improve weather models, forecast droughts, floods, and wildfires. It also helps us get water where people need it. Measuring gravity from space helps NASA better understand the entire water cycle here on Earth. And that can come in handy next time you want a glass of the stuff.
Okay, so let's do the activity. So we need to take these observations from the GRACE satellite mission, and we need to organize it into a way that will allow us to make an interpretation of it. So that's the purpose of making graphs and charts and tables, is because it's easier to look at a summary of the information rather than using each individual picture to make our claim. And so we need to condense it down. And so let's organize it. And so how we're going to do this is we're going to make a graph of the changes in water for just one particular location. And so what location matters a lot to you? Think about that. Maybe it's where you live. What about where you live? And so can you find where you live on the map and only focus on that part of the data? So you can use Google Maps or another mapping software, or if you happen to have a map of the United States that you know where you live at on it, use that to find your place. And then what you're going to do is you're going to pinpoint. I'm going to give you a sheet, and you're going to pinpoint exactly where you're at on all of these images. We're going to put a little black dot on every single one. And then we're going to see if we saw a lot of changes in the amount of water where you live. Okay, and so we're going to do this for West Virginia. So in the Google Drive that I shared with you guys on the classroom, and then I also will put in the link to this video on YouTube, is the sheets for ways that you can print out the data for students to have sheets of data to do. And so I've already done this through the computer, and we'll just start from the beginning. We're going to record the amount of water in millimeters of water for each month in the table for our location here in West Virginia. And so I've already compiled a data table. A data table has column headings that include units to explain what values are and what information is below it represented. So my column headings here are month and year. So I'm going to put January 2003, and notice I did this for every month in 2003. And then this is the millimeters of water that we had each one of those months. And so starting in January, I pinpoint it right here in West Virginia, right in the heart of West Virginia. And I used the legend down here, or the key, to figure out, I tried to match those colors, and it was somewhere around 100, maybe a little less than 100. I probably could change that to 90. Now that I'm looking at it in this presentation view, it's a little bit different. And so it got a little bit darker that time, and so I moved up to like 110 over here. And in March, it's getting a little bit darker. We're up to 120. And then it looks like it got a little bit lighter where I had been marking with the black dot, and the darker regions are moving over in this direction. So in West Virginia, we're back down to like 110, maybe 100. May, I didn't see too much change. It got a little bit lighter in color, so I moved it down to 100. June, still at 100. July, looks like the color got a little bit lighter. Not much lighter, but I put 90. August, you can tell that it's getting lighter in color now, so it's put down here around 90, and maybe could go down to 80 there. September, it definitely got lighter. It's down to 70. October, it's around 80. And it's starting to get darker again in November. Up to December, it gets dark again. Okay, so we've got our data table. So now we need to turn that data table into a visual, which is in the form of a graph. And we're going to do a line graph instead of a bar chart. Even though you could represent this information in a bar chart if you want it, I like line graphs because it shows me the rate of change. And so this is we're expecting things to change. The amount of water is changing. And so I like to see my going up lines, my going down lines, and how steep those lines are. And plus, it's sequential information. The data progresses from one month to the next. So connecting them with a line is showing the sequence, that they're not broken segments of information. And so we're going to turn our table into a graph. And there are a couple, actually 3 options that I'm going to suggest for you to do for your assignment. And I'm going to show you how to do some of them. So the first one is how you would traditionally make a graph. Start with a title. So for example, it could be West Virginia Water 2003. We're going to label the x-axis, the month. We're going to label the y-axis, the amount of water with the units, millimeter of water. And then scaling is going to be the next important part. So you're creating a graph by hand. You want to scale this so that it covers most of the page. It's not too small. It's not too large that it doesn't fit on the page, but it covers the space that you're working in. And so to do that, after you've drawn your line for the x-axis and the y-axis, you need to count the number of lines that you have available, because you want to use the whole space of that line as possible. And so you got to fit every value within that space as well. And so count the number of lines that you have on your x-axis. And since we have 12 months, you need to divide that number of lines by 12 to determine the spacing for each month. So if it happens to be 3, that means every 3 lines, you're going to write the name of the next month. That'll keep it scaled appropriately and cover the entire breadth of the page. Okay, number 2, You're going to do the same thing for the y-axis. Count the number of lines going up that are available to you to use. And if you want, if you haven't drawn your lines yet, you can plan this so that it gives you a nice round number. So what are we doing? Well, our lowest value needs to be on there at -200. Our middle value needs to be there in the middle. And our highest value needs to be there at the top, which is +200. So that's a representation of 400 different numbers that we want to fit on our vertical axis. And so I need to count so that I can get an equal number when I'm dividing. So I would suggest maybe counting 40 lines. Because 40 lines, if I take 400 and divide it by 40, means that each line is going to represent a change in 10. And I like that because it goes along with the information in my data table that I had. Right? I only reported values and differences of quantities in 10. And so that'll help you plot your dots in the right place using the grid on the graph. Okay, so I'm actually not going to demonstrate that by hand in this class session, but if you decide to go that route, if you want help, contact me and I will help you out. We can do a little virtual call together and I can help you through that process. If you want to make some type of graph that you like to use in your classes a lot with kids, make that type of graph, and I'd love for you to share it with us. And maybe I'll learn something new and a cool way to express scientific data as well. So I encourage you to go off script a little bit. These are just suggestions for anybody that might be thinking or struggling with an idea. All right, next is chartgo.com. And so chartgo.com is going to be sweet. This is super simple. And so what I'm going to do is I'm going to take my table and pull it out, and I'm going to go to chartgo.com. And instead of flipping back and forth between the chart maker and my data table, I'm going to split my screen so that I can see both of them. There we go. And so I'm going to just click Create Chart. And the options appear here for chart settings. I can preview my chart based upon what settings I've set, and I can download it into an Excel spreadsheet or a CSV file. And so I'm also going to put in the chart data down here, and then I can hit Create Chart whenever I'm finished. So I'm just going to change this to, wow, there's lots of options. Area pie, I want the line chart type. The width and the height, this is the number of pixels rather than the information that's going into the chart. So I'm just going to leave that alone for now. The title, West Virginia Water Year 2003. Or I can make that the subtitle. I can make this West Virginia Water and put year 2003. The X title, well, that's going to be month. The Y title is going to be amount of water. And I'm going to put in parentheses the units, millimeters of water. Background color, well, since it's water, I'll stick with the blue color. And I want this to be vertical, horizontal, or diagonal. I'm going to leave it horizontal. That's the traditional way of viewing time as it passes from left to right. Okay, title font, I can play around with the font. Let's make it italic this time. My labels, I'm going to leave those normal. Okay, so so just like scaling on like a written graph, you got to scale on ChartGo as well. So the maximum Y value is positive 200. The minimum Y value is negative 200. And what is the threshold line? I'm going to hit this. Threshold, optional, and numerical field. Displays a dotted line on the y-axis. Value must be between lowest and highest y values. Oh, so that's kind of like our 0. That's our threshold. That's where it's just kind of normal and in between. Okay. Do I want a grid line? Transparent? I'll leave the grid lines. Let's see what our legend, yeah, let's see what a legend looks like. Do I want it to show the values? Yeah, that might be neat information to have on the graph as well. I'll leave the border on. Okay, and then chart data. This is where I put in the information. So the X is going to be simple. It's going to be the month. Now I already put 2003 up here in the title, so I'm just going to leave this as January, February, March, April, May, June, July, August, September, October, November, December. And then here are the water values for the Y data. So I'm just going to copy it over 100. And notice how I'm just putting them in lines, like line entries. So January's first, and then I hit enter and went down to February, hit enter, went to March. I'm going to do the same thing with our water values. And that helps it determine the coordinates. Okay, and so those all match up. You can add a second line. So if you want to do like a second month and compare month 1 to month 2, or maybe you want to compare 2 different locations within the same month, you could add a second month information, and then you could, change this to like showing West Virginia and California comparison. Okay, and so group 1 would be the water values for West Virginia. I'm going to leave that as just group 1 for now. And then I'm going to preview this before I create it because I may want to change it. Well, this is neat. So we were above the threshold the whole time. We never went below. That's good information that we can get from this visual. So I kind of like that threshold line being there. That's kind of neat. I'm not sure how to do that on Excel, but I know that I can do it on ChartGo now. Okay, so then you can create the graph if you like how it looks, and then it's copy and pastable. You can download it. You want to change what it looks like? That's what it looks like as a bar chart. Look like as a pie chart. Ooh, that is not a good way to represent this data or these data. These data. I like the bar chart, but I mainly like the line graph. Okay, so that could be one way that you do this. And then if you have Excel, you can just do an Excel spreadsheet as well. So let me show you how to do that. You can also use Google Sheets to do this. It's going to be slightly different than what I'm showing you here because of the position that the features are in. But I really just need to copy my chart over into the spreadsheet. Oh, it didn't copy any of the information. Okay, so we've got month and year. We've got millimeters of water. And so I'm just gonna have to switch my screen here a minute so I can see that information again. Okay, so we've got January, February, March, Oops, that is not the right year. Yeah. Okay, I have my months, and then I'm just gonna put my water values in. And it's super important that you don't put the units in the cell, right? We don't want to put millimeters of water in here with the values. There are two reasons. Number one, you never repeat units in a data table because that actually would change the meaning of the unit, right? If I had inches here and also inches in the header, that would be inches squared, where we'd be reporting like an area rather than a length. So by putting the units in the column heading, you're saying multiply everything in this heading in terms of units by what's in the cell. So that would be 100 millimeters of water, 110 millimeters of water. And so if you change it or mathematically, it's incorrect. And then also, whenever you put it in an Excel spreadsheet, it will not recognize your entry as a numerical value. Instead, it'll recognize it as a text entry, and it won't make it the way that you want in the graph. So let's see if Excel will do this the quick way. So the quick way would be to highlight everything that you want to be displayed in your graph, go to Insert, and then go to the chart types here inside of charts. And we want the line graph, and I want a particular type of line graph. I can pick from the options. I like the data points being identified, so I'll put that one there. Okay, so we have that. It did graph this correctly. Sometimes you don't get the information correctly, especially if you're doing more than an X and a Y. You have to play around with it a little bit. So if you run into problems and you don't get a graph right away, that's correct. You're going to have to schedule with me, and we'll work on it a little bit. And so now I want to click on this graph, and notice that it took me to the design window. I can change. Oh, that looks kind of cool. I'm going to use that theme. But you also want to add chart elements, right? So we want a chart title above the chart that represents our information. So West Virginia water levels for year 2003. Or actually, I already have, yeah, in this case, it's not a bad idea to have them replicate it, because even though, yes, it's here on the horizontal axis, it's different whenever it's dealing with a chart title and the label axes than it is with like putting units here and then also in the column heading. There's no mathematical significance to repeating them. So I'm going to leave it there. I think this better explains my chart, which is why I'm doing that. And then I want axis titles. So across the bottom, I want to say that this is month. And then I want to add another chart element, another axis title for the vertical column. I'm going to double click the text and then delete out until I can type myself. And so I will type in here amount of water. And I don't have millimeters of water anywhere else represented. So I want to type that in here, and I'll put it in parentheses. Okay. And so we've got the title, we've got the axis labels, we've got the units, and we've got the lines connecting the dot, and it scales it automatically, right? It's already scaled it out for us, and so I can change the size of it if I want. So yeah, there we go. That's it. Okay. So let's wrap up class here, now that I've given you those examples. So things you need to do, but try to do before the teleconference on day 3. You need to construct a table for a graph using this data. And so, for example, you can do it for any year. If you want to do January to December for 2004, do that. In fact, if you guys want to post on the stream on our Google Classroom what year you're going to do, so that way someone else will maybe decide, well, I'll do a different year then. That way we can lay them all out and share them with each other and kind of see what's happening. That would be really fun, interactive thing to do. B, you can do just all the same months for the stretch of 2003 to 2012. So if you want to see what's changing in January, how is it just January water level information would be kind of a neat graph to create. You could do a different location on the map that's meaningful for you. So maybe you lived somewhere else before and would like to see what the water table is like there in your hometown or something. Anything you want. Those are just 3 examples of how you can go about doing this. And then number 2, you're going to create a graph that corresponds to the data table. So all that information in the data table is going to be represented in the visual graphical format. And you need to have those specific graph elements that I've been showing you when I modeled mine. You need to have a title. You need to have an axis label for both the X and Y axes. You need to have units when applicable. You need to have a line graph where the dots are connected. And you need to have appropriate scaling. Now, I did say earlier, if you want to show me a different type of graph, you can, and I am totally okay with that. So if you don't want to use a line graph, you can, D doesn't apply to you as much, but make sure that you do create a graph, though, that accurately represents the information. You don't want to make like that pie chart. The pie chart did not really do a great job explaining the progression of the water level change throughout the year. So we don't want to use a graph like that. Use an appropriate type of graph. Okay, and then at the teleconference, we're going to do a pre-writing strategy. Together as a class, I'm going to have you guys participate in that, and that's going to help you understand how to write a description that explains the information that you're presenting on your graph correctly. Where it doesn't involve an interpretation, it doesn't involve a research, it just is stating what the graph is showing. And then I'll give you a chance to draft that out, and then you're going to have someone else in the class proofread yours. That's going to be the journal assignment. So there's actually 2 assignments. There's the project assignment, and then that journaling assignment is going to be the proofreading part of this. And so you need to find and collaborate with somebody. Use the stream to in the Google Classroom to find a partner and to let people know when you've partnered up. And or even just request, hey, I still need somebody to look at mine, and I still need to look at someone else's. Do that there through the stream. That way you can just quickly communicate with each other. And then in that journal entry, you're going to submit screenshots or evidence that you gave feedback to someone else. So you're going to put your own submission, and then you're also going to put the feedback form. So your responses. And so for feedback, check the rubric, because I'm looking for you to provide 3 things. Number 1, I want you to give someone a compliment on something about their writing. Number 2, I want you to give them a constructive suggestion on something, another way they could word something, another word they can use, another way to sequence their description. Those are all examples. Even if it's something that they don't need to do, just give them a suggestion. And then the third thing could be any type of comment. So I'm looking really for 3 things where you've provided feedback in those forms. And so do that, and then submit your feedback that you gave to someone else as part of your journal entry. Okay, I'll see you guys at the teleconference, and we will do the pre-writing strategy then.